Hello, second hour. Yeah, second hour. Good to see you. I am currently with some students at Space Dynamics Lab, but I wanted to make sure you had the chance to go over your test. This is what we do after every test that we take. So hopefully by now you have a Chromebook in front of you. You're logged in to GradeCam so you can see your test answers. We're going to go over it in just a second. If you're not there yet, then I'll have the sub pause the video now. You guys go get what you need, but you need to have your Chromebook in front of you ready to go over this exam. What you see here is our class results. So we had a 74% average. 11 in this excellent, 4 range, call it an A if you want to. 16 here in the 3 proficiency range, 6 in the 2 proficiency, no ones or zeros. So that's really good. This was a good test, I think. Some areas of improvement for sure, but definitely a good test overall. I think you guys should be happy with these results. With that being said, hopefully by now you've seen your score, you've seen your grade, and you kind of have an idea of whether or not you'd like to reassess. And if you don't, well, you need to make that decision probably right about now because we're going to go over this test, and part of the reassessment process is completing what is called a reassessment ticket. And I will show you what a reassessment ticket looks like. But while I pull that up, you need to kind of make the decision right about now on whether or not you want to reassess. Because if you do, you're going to need a reassessment ticket. Okay, here we go. So this is what the reassessment ticket looks like. Maybe I can turn it this way and a little bigger. Okay. I've printed, oops. Uh-oh. This doesn't look good. There we go. So this is what a reassessment ticket looks like. Okay. It's a form that you need to have if you plan to reassess. The goal is for you to fill it out now so that you know right away that what parts of the test you want to reassess. What I'd really like to avoid, if at all possible, is kind of the influx of students that usually happens after a test. You show up to Flex and you say, "Hey, Mr. Adams, I need to get my grade up." To which I will say, "Okay, well, you got to reassess. What do you want to do?" And so you say, "Well, I want to reassess." To which I would say, "Okay, what do you want to reassess?" And then you would say, "I have no idea." I'd like to avoid that. I don't want that to happen. I want to make sure that you know exactly what you want to reassess so that you can show up for Flex or before or after school, whatever works for you. You can show me this form and I will know exactly what you want to do and I'll know exactly what to give you and exactly how to help you. It streamlines the process, makes things easy for everybody, especially me, because there's a lot of stuff I have to do. So let me quickly go through how to fill it out. The first question here asks, did you do the study guide or not? And you know you did the study guide based on if you have a green check mark on your study guide. If you see a green check mark, that means I looked at it and it is complete. If you have a blue circle with a line through it, that means it is incomplete. There was a significant portion that wasn't done, and that's not okay. The one requirement, the one qualification to reassess is to have a completed study guide. So if you're planning to reassess and you have a blue line with a slash through it, or you didn't turn in your study guide at all, that needs to be the first thing you do before you do anything else. If you go through all the reassessment process and turn something in without first having a completed study guide, I'm not going to look at it. So you're kind of wasting your own time. So make sure the study guide gets done. Number 2 says standards. This test had 3 standards that were assessed. Every test has, somewhere between 2 and 4. And so those 3 are momentum slash conservation, weight, and falling bodies. Right over here, these are the questions that are inside of that standard. And right here are the total number of points that were in that section. So you kind of have all the information you need to kind of dissect your test item by item and keep track of how many points you missed. And you can write down what your proficiency was, 1, 2, 3, or 4. Remember the percentage bands are right up here. But again, the idea is by the end, you can get down here to number 3, and you know very clearly I did really well on falling bodies, and I did pretty good on weight, but I really struggled on the momentum one. That's the one I think I ought to do. And there might be more than one that you want to reassess. So you can circle more than one. That's fine. But that's the idea, is to have this paper ready to give to me on the day that you want to reassess. So please pay attention as we go over this test, fill out this reassessment ticket, and we will be ready to go. With that being said, let's begin. Number 1 says, what is the relationship between mass and weight? Okay, we have measured it in class. We've measured mass and weight many times, and we know that if something has more mass, then it also has more weight, which means that this is a positive or a direct relationship. Number 2 reads, when comparing the momentum of two moving objects, which of the following is correct? So process of elimination. I like this question because it's what's called, or at least it resembles what's called a parallel foil. We recently had that ACT debacle, but a common type of question on ACT and other tests like that is what's called a parallel foil, where they'll have very similar sounding questions, but with slightly different words in there and slightly different reasonings. So this is kind of like that, right? I can see more, less, more in different places. And so I need to just kind of read carefully and pick out the one that makes sense, the one that agrees with everything I know to be true about momentum, which is mass in motion. So H says the object with higher velocity will have less momentum. Well, right away, that doesn't sound right at all. So I'm going to X that one out. A says the more massive object will have less momentum. Again, that's contrary to everything I know. I know that more massive things have more momentum so long as they're moving. So A doesn't make sense either. W says the less massive object will have less momentum. That sounds true. And then this last statement here, if the velocity are the same, absolutely, 100%. So I'm going to select W for sure. I'm going to read K just to be sure. The more massive object will have, again, less momentum. That doesn't make any sense. So the correct answer is W. Less mass, less momentum. Number 3 says, which of the following has the greatest momentum? We've got 4 animals, each with their mass given and a velocity. So to find their momentum, we need to multiply their mass by their velocities. So 275 times 0.55, 2.7 times 7.5, so on and so forth, and select the number that ends up being the biggest. And I think, if I'm not mistaken, the tortoise has the most momentum. The tortoise is moving very slowly, but its mass is really big. So it ends up having the most momentum. Number 4, if you stand on a scale in an elevator which was accelerating upward, so that means it's either going up and speeding up, or it's going down and slowing down. Either way, the acceleration is upward. How would your apparent weight compare to your actual weight when standing on a scale in an elevator which is not moving? So if we remember the sensation of an elevator, right, the apparent weight is really all we're feeling. And if we were standing on a scale, what that scale would say. If the elevator's not moving, I don't feel any different. My weight feels normal. The scale would say a normal weight. If I start accelerating upward, I feel heavier, right? If I didn't know any better, I would say, oh, gravity is increasing on me. It's not, but the floor of the elevator pushing up against me is increasing. And so my apparent weight would be greater than my weight when standing in a non-moving elevator. Number 5 says, if a canister's mass on the moon is 65.7 kilograms, what is the approximate mass of the same container on Earth? We have to remember here that mass is an intrinsic property of an object and is not dependent on location, nor is it dependent upon the force of gravity. Mass will remain the same, whether this object is on the moon or on the Earth. So to answer this correctly, part A, I will put 65. Part B, I'll put 1 decimal place. And C, I will put kilograms. Okay. A few of us had issues with part A. Please don't record any decimal places on part A. So don't put 6.7, or sorry, don't put 65.7, just put 65. Number 6, what is the weight of a 132.1 gram baseball glove on Earth? So weight is equal to mass multiplied by the acceleration due to gravity. That's little g. I have to be cautious here because weight is measured in newtons, not grams. Little g is meters per second squared, but mass is measured in kilograms, not grams. So this number is given to me in grams, and I need to change it to kilograms before I move forward with any calculation. To do that, I will divide this number by 1000, or I'll move the decimal 3 places to the left. So I'll do 0.1321 multiplied by little g, which is 10. And so my answer becomes 1.321. That's what my calculator says. To answer this correctly, my whole number, I'll write this over here. My whole number is 1. I am allowed, based on the problem, 1 decimal place. Okay. Remember, little g, we rounded to 10 because it makes things a little more convenient for us. But in reality, the acceleration from gravity on Earth is a very well measured and verified number with many decimal places of accuracy. So I don't need to let little g affect my decimal place. So I'll go with 1 as part B, and part C. The unit of weight is newtons. And there's my answer. Number 7 reads, River and Hawk are discussing the units for little g. To be clear, just so everybody's aware, I am not talking about grams. I am talking about little g, the quantity little g, the same little g that appears in the weight equation. River insists the units are meters per second squared, while Hawk insists the units can also be, okay, I want everyone to read this with me, newtons per kilogram, not newtons or kilograms. The slash there indicates a ratio or a division, okay? For the same reason that the slash in the meters per second squared indicated a division or a ratio. They ask you to help them come to a decision as to who is correct. Provide a detailed description of how you will explain what the units of little g are. Okay, now that we've gotten out of the way this isn't grams, okay, if we go back to the weight equation, which reads W equals m times g. If we remember, this equation is really just Newton's second law. Weight is a force, and it is equal to mass multiplied by acceleration. That tells me that little g is simply acceleration, but it's specifically the acceleration from gravity. And we know that the units of acceleration are meters per second squared. So that makes River correct. River is correct. The units of little g are meters per second squared. But what about Hawk? Well, if we rearrange the weight equation, then we find that little g is equal to weight divided by mass. The units of weight are newtons, and the units of mass are kilograms. And that is newtons per kilogram. So Hawk is also correct. So to answer number 7 fully, I would expect you to state River and Hawk are both correct because a Newton per kilogram is equivalent to meters per second squared. Number 8 reads, a roller coaster climbs up a hill at 4.0 meters per second and then zips down the hill at 30 meters per second. The momentum of the roller coaster and then the answer problems suggest where is it greatest, or is it the same throughout? We know that momentum is dependent on 2 things, mass and velocity. I assume the mass of the roller coaster isn't changing, but clearly the velocity is. And so I would want to know, where is the velocity greatest? Clearly that's going downhill at 30 meters per second. So I'm going to select A, greater down the hill than up the hill. Number 9 reads, if the velocity of an object is halved, how does its momentum change? Based on our equation, momentum is mass times velocity. If this velocity value were to be halved or divided by 2, well, then that would mean I would need to multiply the other side of the equation by 1/2 to keep everything equivalent. So halving the velocity means that the momentum is also halved. Again, that makes sense because we know momentum and velocity have a positive relationship. Number 10 reads, what is momentum? Don't state the formula, but tell me what it is. Remember, this came straight out of the study guide. We said it over and over and over again. Momentum is mass in motion. You could replace the word mass with inertia in motion. Either one would be fine with me. Or you could have said mass that is moving, inertia that is moving, the movement of mass, the movement of inertia. I think they all mean the same thing. Number 10, I think, also brought out quite a few misconceptions. Okay, ask yourself this question. Does an object need a force on it to have momentum? Does an object need weight to have momentum? The answer is no. Momentum is a property of that object. and it is due to the object's motion. And because of Newton's first law, we know that objects don't need forces on them to keep their motion. That can be done by itself. That's what inertia is, the tendency to remain in your current state of motion or in your current state of momentum. That's why the definition of momentum does not have the word force in it, because a force isn't necessary to have momentum. It's only required to change momentum. Number 11 reads, what is the relationship between gravitational force and mass? Well, remember gravitational force, that's the same thing as weight. And we've already answered this question. Weight and mass have a positive or a direct relationship. Number 12 reads, what is the velocity of a 12.6 kilogram object if its momentum is 1,440.0 units? Well, to use the momentum equation, if you're comfortable using the triangle, I highly recommend it. My mathematical formula and relationships tell me that I need to take the momentum of this object and divide it by the mass. So that's 1,440 divided by 12.6. And I get 114.2857143. And I'm sure there's many decimal places after that. So to answer this fully for part A, I'll put 114. For part B, from the problem, it appears I am only allowed one decimal place. And for part C, the units of velocity are meters per second. Number 13 reads, what's the momentum of an object with a mass of 55.25 units? Remember that sometimes I omit units. We are to assume I'm using the standard SI unit. So in this case, I can assume that that units right there means kilograms. Sitting on a tabletop of 1.10 meters high. Well, to find momentum, we have to do mass times velocity. The mass of this object is 55.25. The velocity of this object is 0. The object is not moving. So 55.25 times 0 is 0. This object does not have any momentum, which makes sense because the definition of momentum back in number 10 is mass in motion. And if something isn't moving, then it does not have momentum. So 13a is 0. 13b, you could go with 2 decimal places, or I think you could argue that 0 velocity, maybe that doesn't have any decimal places. So I was okay if you put 2 or 0. And for part C, the units of momentum are kilograms times meters per second. Number 14, a boat with a mass of 325.00 units is moving at 14.00 units. Again, we can assume that this unit of mass is kilograms and this unit of velocity is meters per second. What's the boat's momentum? Mass times velocity. 325 multiplied by 14 equals 4,550. So part A, 4,550. Part B, looks like we can have 2 decimal places. And part C, kilograms times meters per second. Number 15 reads, what is the law of conservation of momentum? Really, it's just a statement of the law, okay? Now, a common misconception that crept up on our test, okay? How do I explain this? The law of conservation of momentum is not the same as Newton's first law. Newton's first law would state something along the lines of an object at rest will stay at rest, an object in motion will stay in motion unless a force compels that motion to change. Or you could say an object with momentum will keep that momentum unless a force compels that momentum to change. That's Newton's first law. The law of conservation of momentum isn't referring to one specific object. The law of conservation of momentum is referring to a system of objects. That means at least 2, because the law of conservation of momentum deals with forces. It deals with an interaction between, again, at minimum 2 things. If there's only one thing involved, then I can't really use the law of conservation of momentum. So what does the law of conservation of momentum state? It states that the total momentum of a system, not of one particular object, but of a system, remains constant before and after a force or an interaction or a collision of some kind. The total momentum stays the same. Does that mean that all objects within that system will maintain their momentum? No, of course not. Forces change momentum. But if one object were to lose momentum during an interaction, then that must mean another object or objects will gain that momentum. Okay. Another way to phrase this law is forces don't create or destroy momentum. They simply transfer momentum from one thing to another. I hope that clears up a little bit of confusion on the difference between this law of conservation and Newton's first law of motion. Number 16 reads, explain the difference between mass and weight. We did really well on this question. I was very impressed. You could have mentioned the definition that they're defined to be different things, and so therefore we measure them differently. You could have mentioned mass is the measure of the amount of stuff or matter or particles. Weight is a measure of force, specifically the force of gravity. You could have mentioned that they're measured differently using different measuring tools. Mass is measured using a balance scale. Weight is measured using a spring scale. You could have mentioned they have different units, kilograms and newtons. You could have mentioned their dependency on location. We did really well here. So if you have questions about 16, please come talk to me later. But for the most part, I think we did really well. Number 17 reads, what is the weight of a crate with a mass of 48.3 units? All right, fairly simple here. M times G, 48.3 times 10, that's going to be 483. That's your whole number. Part B, again, we can go with 1 decimal place here. And part C, the unit of weight is newtons, or kilograms meters per second squared. Number 18 reads, what's the mass of a crate with a weight of 75.7? So my mathematical model tells us that to find mass from this equation, we're going to do weight divided by little g. So 75.7 divided by 10, that's 7.57. So to answer it like a test would want me to, I'll put 7 as my home number. B would say I'm only allowed 1 decimal place. And C, my unit of mass is kilograms. Number 19 reads, what is the weight of a 19.38 units of mass object falling on Jupiter, which has a gravitational rate of approximately 25 meters per second squared? So for this one, I will use the same equation for weight, m times g, but now because I'm on Jupiter, g is no longer 10. It tells me here it's 25. So I'll do 19.38, that's the mass, multiplied by 25, that's the rate of acceleration. I get 484.5. That's a lot of weight. So to answer this correctly, part A would be 484, part B would be 1, and part C would be newtons. Okay. You can ask yourself if how much weight would this object feel? The answer would be 0. It's in free fall. All right, number 20, explain why mass is more useful than weight for measuring matter. Again, we did really well on this one. A lot of you talked about how mass is really more appropriate because it actually is kind of defined to be a measure of matter, whereas weight is not. Weight is defined as a measure of force. But I think the best answer is mass is not dependent on location. If I were to move into even a different part of Earth, technically speaking, if I were to climb a really tall mountain, technically I weigh less at the top of that mountain. Now, maybe not by an appreciable amount, but technically I do. We know that astronauts aboard the International Space Station have a weight that's about 90% of the weight they would have here on Earth. So that was my favorite answer, was mass does not depend on location, but weight does. Number 21, conservation of momentum problem. From what I saw from your answers, I could kind of tell that a lot of us started out well and then maybe forgot to do 1 or 2 things near the end. So if we set this up like we're supposed to, we're talking about a conservation of momentum problem. So we know that the total momentum before must be equal to the total momentum after. So the momentum before is simply the sum of the individual momentums. So I can take their mass times velocities respectively. I'll just call it m1 and m2, v1 and v2. And that's going to be equal to their combined masses multiplied by their final rate. Okay, and I combined their masses because it says in the problem that these train cars couple together. So it's like they're moving off as one bigger object now. At this point, it's just a matter of plugging in what you know and solving for what you don't know. In this case, I know that this term here goes to 0 because the second train car wasn't moving before the collision. This term here, 42,000 times 10, is 420,000. The combined mass I don't know because I don't know the second mass, but that's not a big deal. M1 is 42,000. I'll simply just put M2 for now. The final rate says 6, so now it's a simple math problem. Solve for M2. If I divide both sides by 6, 420,000 divided by 6 is equal to 70,000. And I think that's where quite a few of you stopped. You said, well, the mass is 70,000. The question doesn't ask what's the combined mass of the cars. It asks what's the mass of the second train car. So we have one more step to do right down here, and that's to subtract M2 from both, or sorry, subtract 42,000 from both sides. So 70,000 minus 42,000 is equal to 28,000. So to answer number 21, A would be 28,000. B would be one decimal place, and C would be kilograms. Number 22 reads, if the mass of an object on Earth is 15, what is the mass on the moon? It's 15. So A, 15, oops, sorry, 15, B, 0, and C, kilograms. 23 reads, Clark places a wooden block and a bucket of water side by side on a scale and records the total weight. He then places the wooden block in the bucket so it floats in the water. What will happen to the total weight? It's tempting to say less, right? Because now we're thinking, well, the block floating in water isn't really pushing on the scale anymore, so it might weigh less. But it's not. If we really think about it, we didn't remove anything off the scale, truly. Because if the wooden block is being pushed up by the water, that must mean that the block is pushing back down on the water with the same force, which means that it's getting pushed back on the scale as well. So the weight will stay the same. You can try this at home if you want. Only a few more to go. Number 24, we've got some students investigating how objects fall, and they found some smooth spherical objects that had similar shapes, but different masses. They numbered them, 1 being the lightest, 5 the heaviest. They dropped them from the roof of the school to see how long it would take for them to reach the ground. The students recorded the results in a table. What do you think would be the closest, or what do you expect here to be the closest to reality, right? What you would expect. And we know that we know about Galileo's law of falling bodies, the idea that the acceleration due to gravity, which we call little g, ends up being constant for all objects, regardless of their mass. On Earth, it's about 10 meters per second per second. Why is it constant? Right? Because we've talked at length that mass is directly proportional to weight. Heavy or bigger things, things with more mass, are pulled on more by gravity. And normally things that are pulled on more accelerate more, but they don't. But that's because little g can be expressed also as a ratio of weight to mass. And items that have more mass also have more weight. Those that increase on the top of that ratio and the bottom have a canceling out effect. Objects with more weight are pulled on more by gravity, but they also have more mass, so they have more inertia, and they resist that pull more. So I expect S to be the closest to what these students measured. All objects, regardless of their mass, fell at the same acceleration rate. Number 25 reads, describe Newton's second law of motion in terms of momentum. Again, this was one we kind of struggled with, okay? A lot of us resorted to Newton's first law again. I'm not entirely sure why you remember Newton's first law so well, because it popped up over and over again, and you kept kind of sliding it into places it really didn't belong. So let's kind of get that out of the way. Newton's first law is objects at rest stay at rest. Objects with momentum keep that momentum unless acted on by a force. That's Newton's first law, not what we're talking about here. Newton's second law originally looks like this. Okay, it's an equation, but it really means that an object's acceleration is directly proportional to the force applied to it, and it's inversely proportional to the mass. It can be rewritten as force equals mass times acceleration. I've shown you this before. Acceleration is the rate of change in velocity. Mass times change in velocity, that is change in momentum. So Newton's second law reads that force is equal to the rate of change in momentum. Okay? To state this maybe a little better or a little more clearly, What this says is that if the force impressed on an object is larger, then so will that object's change in momentum. Now, I want to be clear here. Again, we've said before, an object doesn't need a force to have momentum, even a big amount of momentum. A force is only required to change momentum. So, to state this problem here, number 25, totally correctly, I would say something like, the bigger the force on an object, the more that object changes its momentum. I hope that makes sense. 26, if a bicycle with a weight of 70.6 newtons is traveling at a rate of 5.49 units, what is the bicycle's momentum? Momentum is mass times velocity. I know the velocity right here because it tells me rate, but this is not a mass. That is a weight. I can't just plug that number in, but hope is not lost. I can use this number 70.6 to get mass. Mass I know is equivalent to weight divided by little g. So 70.6 divided by 10, that's 7.06 kilograms. So that's what I'll plug into my equation. 7.06 multiplied by 5.49. And I get 38.7594. So part A, I'll put 38. Part B, I'll put 1. And part C, kilograms times meters per second. 27 reads, explain which cross-cutting concept is a good match or fit for someone who is investigating the law of falling bodies. If you recall in the study guide, when you filled out page 3, there really wasn't a wrong answer. You could pick any cross-cutting concept. It's whatever you felt was the right fit. So the same applies here. As long as you picked a cross-cutting concept and gave me an explanation, you got full credit. And I think it was worth 2 points. Okay. As long as you put a cross-cutting concept, so cause and effect, patterns, systems, energy and matter, whatever you thought. Same with number 28. Number 28 reads, which science and engineering practice is a good match or fit for someone investigating the law of conservation of momentum? And again, an explanation. So all you had to do was pick one science practice, planning and carrying out an investigation, analyzing data, developing models, anything you felt like you did, and then add on an explanation, and you got your 2 points. Okay, well, that concludes the test. Good work again. I will see you all on Monday when we will begin our new unit.